All right, so welcome to our fifth lecture. Today we're going to talk about the convolutional neural network, and we'll talk about why the regular neural network is still not sufficient for a certain type of task. We'll talk about what it does, why it does it, and why it's suitable for a specific task. Let's first watch this video. You're probably familiar with it, but Tesla's autopilot. And on the right side of the screen, we can see what the computer is seeing. It's a video and being fed in as input, and it's describing what it's seeing. So those bounding boxes that you see, those are like it's finding that, okay, this is a car or this is a stop sign. And given that input, you can see it's making certain decisions. Should I drive? By how much should it steer the wheel? And this is almost certainly using a convolutional neural network. And the reason for that is, we'll talk about it, but the convolutional neural network is extremely suitable for image tasks. Images are really well built for the convolutional neural network. And videos like the sequence we saw over there are just sequences of images. So a video, like 1 second of a video might be like 30 images or 60 images. And so we can use machine learning on the specific images, but in sequence. And so let's say we have some task, and again, primarily convolutional neural networks are used for images, videos too. That's where they're really accurate and they're really good in those particular tasks. So let's say we want to classify if an image is a face or not. We have our database, or we have a bunch of data of images. Around 50% of those images are going to be images of faces. The other 50% are going to be images of not faces. So it could be like random images. The task is going to be image classification, let's say. And this is a classification task. And so we want to predict, okay, is this an image? Is this image a face or is it not a face? And of course, this is a classification task. And so we have a 0 for it being a face and 1 being not a face. And this is the same thing as a regular neural network. All right, so let's talk about how humans perceive vision, how we see images. All right, so playing off the Tesla theme, we see an image of a Tesla car. We might view this image by the features that it has. For example, we can see, okay, it has a wheel, right? Almost every car has a wheel to it. And so that's one feature that we extract that tells us that, okay, this is a car versus it not being a car. Well, there might be more than one wheel, okay? There might be some headlights, that's another feature. The overall shape of the car tells us, it might be a feature that tells us if this is a car or not. And maybe the color or all these types of features can tell us can help us classify if this is a car or not. This is how we see relatively, right? We have image as an input, and we want to classify, is this image a car or not? All right. So there might be, so in the 80s, in the 90s, people wanted to give computers the ability to classify images. They wanted an image to say, is this a car or not? Or is this a face or not? And this actually has a lot of applications. For example, self-driving cars. For example, every time you open your phone, you unlock your phone with your face, that's an image classification task. And that most likely has also a convolutional neural network. So in the 80s and 90s, people were like, okay, how do we design a computer, or how do we design a program that can classify an image or not? And so they kind of started off with thinking, okay, well, humans think of images, they classify images using features. They see, does it have a wheel? Does it have the shape, overall shape of the car? And they use this collection of features to distinguish is it a car or not. And so what they did was they're like, okay, let's program. We can kind of see what a feature is, right? A wheel feature is going to be relatively circular. We expect that. The shape of the car is going to be relatively rectangular. And so we can program those features in, and we can program a computer and we can tell it that, okay, we want to have it rectangular, or we want it to have a wheel. And if it has these specific features, then classify it as a car. If it doesn't have it, then classify it as not a car. And so people were using their inbuilt human knowledge to try to classify images and try to program that into a computer. The problem with that is there's a lot of different types of images and of the same car. For example, the viewpoint might be completely off. We might, for some reason, have a flipped car. Well, now it might be difficult to classify, oh, well, maybe this is kind of difficult to say that this is a wheel. Even though us humans, we don't have too much of a problem classifying this as a car, a computer is going to have a relatively difficult time if we just program in features. Like if we just tell it, okay, we're just looking for the shape of the car, we're just looking for some wheels. If it's flipped, it's going to have some problems with it. Same with if the scale is off. You might have a picture of a really small car versus a picture of a really large car. Even though these are the same picture, but it's going to be difficult for a computer to understand that these are the same pictures because we're telling it that, okay, these are the features you should look for. Same with the different types. There's different types of cars and with different shapes and different structures to them. And so how do we program, how do we hand code all these features to all the millions of different types of variations that could happen? And this is actually a really difficult problem. And they found that in the 80s and 90s that this is not the best way to do it. And so, well, the neural network came in, and in the 2000s, 2010s, neural networks, because of the vast amount of data, the vast amount of computation, they've been really good at classifying, at finding the relationship between inputs and outputs. And so we did this in the second lecture where we use a regular neural network to classify an image. We had the handwritten images and we wanted to classify, okay, is this image the number 6? Is this image the number 5? The way we did that was we took this two-dimensional image, right? An image is pixel data. We took this image data, which is two-dimensional in nature, and we flattened it out. We took this 2D array and made it one-dimensional. Okay, it worked for us. We got like a 97% accuracy, I think. Pretty good accuracy. The problem is we will find out that if you go into more complicated image tasks, like a self-driving car, like detecting faces, that gets harder and harder to do because maybe faces are more complicated than handwritten digits. And so the regular neural networks will not get as good accuracy. Maybe eventually they will if we give it a lot of training data, a lot of computation, maybe it'll do it. But a more efficient way is to use a convolutional neural network. And the reason for that is because, or the problem with a regular neural network is because we flatten out all our pixel data. Our pixel data is two-dimensional and we're making it one-dimensional. Well, all spatial data is lost. What do I mean by that? Okay. Let's say we have this 3x3 area. This is a particular subset of the image, right? This might represent a car, a wheel, sorry. This might be a wheel, let's say right here. Okay, well, if we flatten this image out, this particular portion of the image, we can't really see it as a wheel, right? It will be some like vector, it'll be some array. And then we're gonna lose the data, the spatial data for this, right? Because this wheel is gonna be divided up by pixels if it's a 2D array. Converting it to a 1D array is gonna lose all this spatial data. And by spatial, it means because this particular portion is below this particular portion, right? Maybe the upper part of the wheel is above the lower part of the wheel. If we flatten that out, there's no way we can know with which position. We won't be able to tell the upper part of the wheel compared to the lower part of the wheel. And this might not seem important, but it is, because we images, the way we see it is by spatial data. We don't see a wheel flattened out. We see a wheel in 2 dimensions. And so that's the problem with a regular neural network. It just loses all the spatial data. The solution is the convolutional neural network. And the convolutional neural network can actually model this spatial data. Okay, how does it do this? And what do I kind of mean by that? Well, the regular neural network takes in 1D inputs, right? We have inputs, it's multiplied by the weights to some particular output with the hidden layers. By definition, this is a 1D array. It's one-dimensional data. And like we said in the last slide, 1D data is not an image. An image is 2D data. So what the convolutional layer does is it can model for this. And instead of taking a single input like the regular neural network does, is it takes a set or a collection of the inputs. Okay, how exactly does this do this? Well, let's compare it to the regular neural network. The regular neural network would first take this first pixel, and that would be the first input. The second pixel would be the second input, and so on. Okay, the convolutional neural network, on the other hand, takes the collection of inputs. So it's going to take the square, this collection of pixels, and that's going to be mapped out as an input. This, if it's not obvious, is really beneficial because it allows us to map for spatial data, right? We have, let's say the wheel is right here. Well, it's going to take a portion of the entire wheel. And so it's going to map out the wheel. It's going to map out the subset of that image. And this is really beneficial to us because we want to map out the spatial information. We want this spatial data. In the regular neural network, we were losing all of this spatial information. But now, because we're taking a collection of inputs, we can see that we actually have let's say, the upper bound, the upper part of the wheel and the lower part of the wheel. We have that information now, and we can model for that. We can learn from that. And so the spatial data is not being lost like in the regular neural network. And this also allows for automatic feature extraction. What do I mean by that? Well, we talked about like in the 90s and 80s, they were trying to pre-program. They were trying to hard code features into the computer. And so they were telling it like, okay, this is a wheel and try to find this wheel. Okay, try to find the other portions of this image of what we're trying to look for. Well, the neural network does this automatically for us. But now, because we're modeling for spatial data, we can take the collection of inputs. And so we're taking a collection, and because we're taking a collection of these inputs, we can automatically extract the relevant features. For example, we have the feature of a wheel. right, in this particular area? Well, mapping for this, because we're taking the spatial data, we're extracting the features of what the wheel is. And so we're taking the features that make an image because we're mapping for spatial data. Again, if you have any questions, feel free to interrupt. But let's look at, this is taken from an MIT course, but it's a good example because let's say we have some task. We want to determine if the image is an X or not. So we can see when we look at the left image, this is an image of an X. And let's say the number 1 represents the color white and -1 represents color black. Well, we can see we're looking at this. This is the letter X, right? Let's look at the right image. We can see that it's for sure different from the first image, but it's still an X. This still qualifies as being an X, right? We can see it looks pretty similar to an X, and we want this to be considered the letter X. Okay, well, now there's going to be similar features between these two images. And what features, just like in a car, right? We have similar features between different cars. The car has a wheel. Most cars have wheels. Same with this, the letter X. There's going to be similar features between the two different images. And we want to learn these features automatically. We don't want to hard code these features. We want this to be learned by the neural network. And so let's look at an example of what these features have in common. This first image is going to have, usually on the upper left side, it's going to have this square where it's going to have these two white pixels right there. Well, the other image, the other X, has a similar feature. They have actually the same feature, right? They're going to have this square with the same amount of the area is going to be the same essentially. The image, the subset of the image is the same. Same with this subset of the image is similar to this subset of the other image, the first image. And so using these collection of different features, and this is kind of like the subset is a kind of a feature of what an X is supposed to be. An X is supposed to have these features because we use these features to determine is this an X or not. And so these collection of features are going to be learned by the neural network, and it'll learn like, okay, an X usually has this 2x2 collection, this arm branch right over here. Same way, it's going to usually have this 3x3 similar features, and it's going to learn those features and extract those features. How does it do this? How is it learning what features are relevant and which are not relevant? It does this similar to a regular neural network. A regular neural network learns specific features by the weights. As gradient descent flows, as it's learning, well, the relationship between the inputs and outputs are learned. And so it's extracting relevant features from this. The convolutional neural network is doing the exact same thing, but just with two-dimensional data, just with spatial data. And by spatial data, I mean the image data, by two-dimensional data. And so it's doing it a little bit differently, but not really. All it's doing is, remember, in the convolutional neural network, we have a collection of inputs. Instead of just a single input, we have a collection of them. So we're gonna have a collection of weights. What do I mean by that? Let's say our feature, our spatial our facial feature is this 3x3 area, this 3x3 subset of the actual image. Then our weight is gonna be this 3x3 weight filter, essentially. To compare this with the regular neural network, we had, let's say, just one input. This would be mapped out to the output multiplied by a single weight. And this was just an integer, it was just a scalar value. The convolutional neural network, on the other hand, it's the same thing. This input, though, is, instead of being one input, it's the collection of inputs. It's the subset of the image. But that's going to be mapped out, and this weight is going to be a collection of weights, or a matrix, or an array of weights, a two-dimensional array of weights. And the values, we can see it's like -1, 1. It's learned using, it starts off randomly, just like a regular neural network. And as using gradient descent, those values are learned. And those weights are important because those are what extract the features. Those are what are being, those are what help and what make the features be learned. Just like the regular neural network, but just with two-dimensional data, with two-dimensional inputs. And so the way it's doing this is we have our learned weights right here. It's our 3x3 weight matrix or weight array. That's going to be multiplied by the subset, or the subset of the image. For example, this is going to be our pixel data right here. This is going to be our image, our image of our X. This weight matrix is multiplied by the pixel values of our image of the 3x3 subset. Because our weights are 3x3, it's going to be multiplied by the 3x3 subset. And the way it's doing this is just matrix multiplication, but we get an output of, well, it's kind of a dot product actually, because we get an output, we get a single output. And this single output is the output of our specific neuron in a specific layer. But this single output is dependent on the pixel data and the weights that are learned. And it doesn't randomly, by the way, it doesn't, I'll talk about this later too, but it's not like randomly choosing a specific portion of the image. It's systematically going through the entire image and multiplying the same weight matrix to every single portion of the image, and then getting the corresponding output. And this is a really good video of what exactly is going on as it's flowing through the image, because it has to go through every single portion of the image. And so after every single portion, it gets a specified output, and that specified output, the activation function is applied to that specified output. And so we get a specific value of whether that neuron fires or not. And so we have our image, it's the letter A, and the subset of the image is going through, it's applying a convolution. It's going through every single part of the image, multiplying the same weight matrix to every single part. And then it gets a corresponding output to what that is. And the corresponding output, well, that's what the features are. Assuming the weights are learned and they're good weights, that's what the features are being learned. And for example, in this particular example, it's the letter A. It's learning that, okay, all the A's have this specific part to them. Maybe they have this empty portion in the middle, or they have this little, they have this bottom part right here, and all A's have that. And the way, again, it's learning that is by the weights, by the learned weights. But it's applying those weights to every single portion of the image. And then the output of that is kind of a new image, right? We can see here, after it after it did all the weights, after it multiplied every single part of the image, it outputs a kind of a new image. But the values, the color values of these are dependent on what those weights actually are. And so we can kind of look, when we actually look at what the image it's outputting in a specific layer, well, we can see what features it's paying attention to. And so in this particular video, we can see this specific layer is paying attention to the bottom part of the image. And so it's learning, and also with this particular areas. And so it's learning that, okay, an A has this particular feature. And the different layers extract different meanings behind these. They extract different spatial information, just like a regular neural network, but it's spatial this time. It's 2D information. Yeah, any questions right now? All right. So like I kind of talked about, each weight corresponds to what the specific layer is extracting, what feature is it learning. For example, and of course we can have as many layers as we want, but each the corresponding weights they extract something, and depending on the type of layer it's at, it's gonna extract some portion of the image. For example, this layer, this specific weight might sharpen the image. This particular weight might detect edges. It might extract edge information. This particular weight might extract really strong edges and might really try to find the edges in an image. And generally, this has been researched that generally the low-level features are first extracted. So for example, in the first couple of layers, the lower level features are extracted. So example, edges, dark spots, those are extracted in the first couple of layers. The mid-level layers, so maybe 3 or 4 layers in, actual mid-level features are extracted. For example, eyes or ears or noses. And this is particular for facial data, but it's the same with other information like car data or letter data. And then the higher level features extract more complicated types of features, more complicated data. And so they might extract the facial structure or the overall metrics of what a face is. But as we go through the layers, we can see they start off extracting these lower level features and they go on to extracting these higher level features. And again, the way they're doing this is using the learned weights. They're being multiplied. They're applying the same weights to every single portion of the image. And they're getting the corresponding features. They're extracting what is meaningful, and they're learning what is meaningful and what is not meaningful. So how do we actually implement this? Again, in TensorFlow, it's very simple. We have the tf.keras.conv2d. The reason it's conv2d is because we can actually feed in also 3-dimensional data or 4-dimensional data, I believe, or even 1-dimensional data. Although that kind of lowers the value of a convolution when you just give it 1-dimensional data, but you could do it if you wanted to. But for image data, it's 2-dimensional, and so we'll do a conv2d. All right, and then we specify the number of neurons that it has, just like the regular neural network. But there's more variables actually that we can specify, we can change. And there's this kernel size over here. Okay, what exactly is that kernel size? That's the size of our feature extractor. For example, if we specify a 3 by 3 kernel size, then it's going to apply a convolution of a size 3 by 3. For example, we have the 3 by 3. Whenever it gets to this portion of the image, it's going to be a 3 by 3 subset of the image. For example, the 3 by 3, well, it's going to take in the 3 by 3 inputs, and then it's going to go to the next portion of the image. And in this particular image, it's a 4 by 4 kernel size because we have 4 pixels are being, the collection of variables is 4 by 4. The collection of pixels is a 4 by 4 value. And then, of course, the weights are being multiplied to this entire area, and then they're being fed as inputs, as singular inputs, to reconstruct the entire image. And the formula for this, if this is kind of confusing, don't worry about it too much, but the formula, the mathematics behind this is we're going to have a double summation. Why is the double summation? Because we need to add up the rows and the columns. And so this formula is for a collect kernel size of 1 by 4. And so we're going to have a 1 by 4 feature extractor. So, or sorry, a 4 by 4 feature extractor. But so that corresponds to this portion of the image right here. It's going 4 by 4. Okay, well, we want to add up for this particular pixel, for this particular portion of the image, we're going to multiply that by the one. So this is area. This is the 1 by 1. So element 1 of 1, or the first element, the first row element of the first column element. That's going to be multiplied by the first weight element, the first weight row element, by the first weight column element. And so this corresponding weight element is multiplied by this corresponding pixel element. And so just like the regular neural network, there's really nothing different except that we have 2D data. And the way we're modeling for this 2D data is by this double summation. Because we have a row, we have a column, and so we need to add up those particular positions. And we want to get those particular areas for that. All right. We can also have this strides there's this other variable, strides. Strides is we have this 1 by 1 stride. And we kind of talked about, but how the convolution or the way it moves from the beginning to the right and then to the bottom and then all the way, it's applying the weights through the entire image. Well, we can specify by how much it wants to move by. So let's actually change this to be 2 by 2. And let's say our feature is or the kernel size is a 3 by 3, let's just say, and the strides are 2 by 2. Well, let's say we just start here just to make things look nice. So we're going to start off right over here. We're going to apply our weight matrix to this particular area. And it's 3 by 3 because we specified it to be 3 by 3. Okay, well, our strides are going to be 2 by 2, let's just say for this example. So instead of it moving right over here, which is where if it was 1 by 1, it would move right by 1 and left by 1. Instead of doing that though, it's going to move. So it's going to start off right here, right? Right over here. It's going to move actually by 2. And so it's going to move, it's going to skip this area, this portion of the pixels. In some cases, this might be helpful for some particular tasks, but this is just to show that, okay, this can be done. And okay, this is a really good picture of the structure of our what our model might look like. We start off with our image data. We have our image, a two-dimensional image, let's just say, of let's say it's a car. Okay. And to relate this to practical terms, we establish our TensorFlow model just like in a regular neural network. This next layer is going to be our convolutional layer. And the way we do that is model.add layers.conv2d. And this is the number of neurons. Again, there's really no way to, you just have to experiment and find out what number of neurons are good or not. But for this particular case, let's just say 256. Okay, our kernel size, we're just specifying to be 3 by 3. Our strides 1 by 1. And our activation, our ReLU activation. Just like a regular neural network, except this kernel size and the number of strides. Okay, well, actually I seem to have skipped these slides, okay. Because we have this corresponding, another layer that we have. Yeah, so we have a different layer actually. And so actually, let me skip this max pool 2D. I'll talk about that. But we're gonna skip this part, ignore this part for now. But we'll go to our second convolutional layer, and it's corresponded to this conv2d again. But this is gonna be our second convolutional layer, right? Our first one is right here, and our second one is right here. And again, the number of neurons, the kernel size, the strides, and the activation. You don't really have to specify the kernel size or the strides. I don't think it matters too much, but just to let you know that you can specify it for your particular task. Again, skip this max pool for now. Skip this one for now, this operation. But let's look at this flatten. What does this do? Well, for our regular neural network, let's say it's a classification task, we want to transfer this. We want to learn the two-dimensional spatial features. And we do that, right? We do that in our first convolutional layer. We do that in our second convolutional layer. But then we want to now output a prediction. We want it to say, okay, is this a car? Is it not a car? Is this a face? Is this not a face? Well, for that, we use a regular dense neural network. But remember, a dense neural network can only take in one-dimensional data. Right now, what we have is 2D data. It's image data. It's two-dimensional data. And we need our neural network to input one-dimensional data. The way we do this is by calling a different layer called flatten. And what this does is it takes this two-dimensional data and makes it into one-dimensional. After it's one-dimensional data, we can call our next layer, which is going to be our regular dense layer. And let's say it's at 256 layers. And then we can have as many dense layers as we want, but the actual thing that we want is the predictions. And let's just say we have 256 predictions. That's going to be our last layer. And because there might be 256 classes, let's just say. But this depends on the task. Okay, now let's talk about what this max pool is. What exactly is happening over there? So yeah, so many times, so actually, yeah, convolutional operations and the convolutional neural network is pretty computationally expensive. It's not too obvious, but we're doing a matrix multiplication for every single stride, or we're striding through the entire image. We're applying the matrix multiplication. We're applying linear algebra. We're applying different operations to each stride. And we're doing this for every single image, for every single epoch, for every single iteration. This gets computationally intensive. Mainly the reason for that is because image data is pretty large. For example, let's say we have an image that is 256 by 256. That's a pretty large image. And if we're going through it, like let's say 3 by 3, that's going to take a while. And a common layer, a common operation that is done to improve this efficiency, and this does sometimes help with accuracy as well, is apply a pooling operation or a max pooling operation. And what this does is it allows for the convolutional layer to still extract features, but the size of the operation is going to be decreased. Okay, what do I mean by that? Let's say this image is let's say this picture is an image. It's a cat image, or it's a face image, let's just say. It's someone's face. We have our corresponding pixels, and we can see that this is a 4 by 4 image. In practice, obviously, there's images at the minimum are I think 28 by 28, but at the maximum can be like 1024 by 1024, something like that. Okay, well, we established that a convolutional operation going through this image can be kind of computationally expensive. And so we want to downsample, or we want to take this 4 by 4 image and decrease its size. And let this when we do the max pooling operation, the output is going to be a 2 by 2 image or a downsampled image. And okay, what exactly is it doing? This is after the max pooling operation, the max pooling layer. Okay, well, what exactly is it doing? Okay, it's specifically for max pooling. There's different types of pooling, but specifically for this max pooling, it's taking this 4 by 4, okay? And then let's actually, there's different variables for this as well, like pool size 2 by 2 and strides 2 by 2. Strides we don't really care too much about, but the pool size we kind of care about. Because let's say we have a pool size of 2 by 2. This means we're going to divide up our image into 2 by 2 areas. So it's a 4 by 4 image. We're going to divide this image into 4 areas. Why? Because we can see this first area. Area number 1 is going to have 2 rows or 2 elements in the first row and 2 elements in the first column. And so it's a 2 by 2 area, 2 by 2 matrix, essentially, this particular area. So what specifically the max pooling operation is doing is it's taking the max pixel, it's looking at this 2 by 2 area, and it's saying, what is the max pixel? What value is the maximum? And we can see the maximum is the number 6. And it's saying, okay, I'm going to keep that number 6 into my new image, my new downsampled image. And so it keeps the maximum image. It then looks at the next area, the next 2 by 2 area, which is the number 8, and it keeps the maximum of that specific area. And it does this for all the areas in the image. And this has been found that this kind of keeps the image data. It keeps what an image is, but getting rid of a bunch of data, a bunch of the pixels are gotten rid of, right? We no longer have these 3 corresponding pixels. But this does help, first of all, our convolution, because now we have a decreased image size, but we also have this also relatively keeps what our image looks like, or the features behind the image. There's different pooling operations. I specifically talked about the max pooling, but there's also average pooling. And you can kind of guess what it does. In this specific area, it averages everything. So it's going to do 1 plus 1 plus 6 plus 5 divided by 4, because there's 4 different elements. And that's going to be the corresponding element in this. So details aren't too important if you didn't understand it, but understand that all max pooling is doing is decreasing the size. We start off with a 4x4, it decreases that to 2x2. It's decreasing the image size. And this helps with efficiency, it helps with computational intensivity, and this is important for our model. So let's go back to our image, to our bringing everything together. We start off with our image data. We then apply our first convolutional operation. Then we apply our max pooling operation right here. And what this is doing is it's taking this image and downsampling it, making the image smaller, making the outputs of this convolutional operation, this convolutional layer, it's making that smaller. So then we apply our second convolutional layer right over here. And then we apply another max pooling operation. The layers are, I kind of randomly selected them. This depends on your task. This depends with experimentation. But just to show you what this image corresponds to in code. And so, yeah, we're applying the second pooling operation. And that corresponds to this layer right here. Like we talked about, we flatten the image just so we can feed it into the dense layers. And sorry, I made a mistake in the previous little bit later, but yeah, this is going to be the last layer. And this is going to be the number of classes we want to classify. If it's face data, we have a 0 or a 1. Is it a face? Is it not a face? And so we'll have two classes right here. And because we want a probability, the activation is going to be a softmax. If this was a regression task, the activation would not be a softmax. It would be like a linear softmax, a linear activation, just like in a regular neural network. But this is just to bring everything together and to see that, hey, we can use a convolutional network in combination with a dense network. Just like we kind of did that with the recurrent, with the LSTMs. But just to show that there's different operations, there's different layers, and they can be in combination with another. And so in summary, we learned about the convolution or the sliding window, which extracts spatial features. It starts at the first top of the image, slides its way across, applying the weight matrix, and then that gets the corresponding new image, basically because it's extracting relevant features doing the convolutional operation. And we also talked about the max pooling operation or the average pooling operation, which downsamples the input, makes the input into a decreasing size. And that's pretty much it for this. We'll actually apply this in the next lecture. Feel free to reach out if you have any questions, but that is it for this lecture.